Welcome to math. Does everyone have paper? Does everyone have clean paper?
There's some here.
There's paper here. Got pen here? Cool. Take my shoes off. Get in the zone. Cool, so just like a little bit of a, not so much a recap, but just a bit of a reminder of what we were looking at last week. We were looking at sort of bases, number systems. We were looking at a bit of binary, a bit of hexadecimal, and then some just arbitrary other ones, if everyone remembers that. I'll probably do a Kahoot or something, but I might save that for when there are actually more than 5 of you guys here, if that's all right. I mean, it'd be nice and like really competitive if it was just you 5 competing with each other, but anyway. So today the thing we're going to be looking at is... Sorry? Oh, you want the Kahoot today? The topic we're going to be learning today is going to be... Oh, that's very faint. Whoa. What did I hit? Oh, it's opaque. And that's a very difficult color for you guys to see. What's going on with my... There we go. Cool. Today we're going to be covering logic. Woo! Who here's done any logic stuff before? Yep, sweet. You did it... you've done it, of course. You've done it at uni, when you did uni for a little bit? Was it like discrete math logic? Yeah. Yep, okay, cool. So you're probably going to be on board with this. So, like, either of you two, what are some types of like logic operators that you see absolutely everywhere? Woo! And I'm really, as you can tell, I'm really pumped today. And, or, and, not. Cool. And there's also a few weird ones. Like, yeah, let's do XOR as well. Have either of you looked at the textbook for today? Okay, cool.
I didn't want to be too far.
Good. I think you already are though. But the textbook, I mean, and this course, the only thing we really go into is and, or, not, and XOR. We don't really go into a whole lot more. I think the one other one we sort of do is implies, which is a little bit of a curveball, and we'll see why. But those are the main ones we're going to be looking at. Now, let's think about what an AND does. I like to think about them like sort of channels, like pipes or whatever. So you've got 2 things kind of going in, and you've got your AND, which I'm just going to do. I don't actually remember what the symbols are, so I'm just going to put a box with AND here. There's like electrical engineering symbols for all this crap. We're going to have an A and we're going to have a B. Actually, no, I'm going to make it logic things. I'm going to make it P and I'm going to make it Q. Sorry? Dude, it's meant to be way different from this. Mine's so wrong. Wait. Sorry? Yeah, the way it's meant to be is like... Now, correct me if which one it is. So there's this, and I can't remember whether it's this one or whether it's this one, because one of them's and one of them's or. Straight is and?
Or is more triangle, no?
Or is a triangle?
More pointed.
Okay.
I thought or was the curved semicircle at the bottom, like the curved part.
Oh, like sort of like that?
Yeah, sort of like that.
Okay, well let's go with that notation, because the notation's not really like, we're not doing electrical circuits. We care about the symbolic representation. So this is just temporary, right? So P and Q, these are the 2 like inputs, if you will. And we say P equals 1 and Q, lowercase q, equals 0. We're going to put these in. They're going to go in through, I guess I'll just gesture. I kind of want to draw this for people, but they go in through here and here. 1, 0, and kind of like chugs away at them. And what comes out the other end? 0. Exactly. 0 comes out the other end, right? How about if Q was 1 instead? What would sort of come up the other end? Yeah, 1. Sweet. So it's going to get frustrating if I write out every diagram sort of in this, I guess, electrical engineering sort of way. So I'm actually going to start to write it as a logic statement. I'm going to say P, I'm going to say and as this, Q. So this, oh, no, not with an A there. This, we're going to, oh, God damn it. Yeah, caught myself that time. This, we're going to define as and. Yep, and that's how we can remember what the symbol is, because it's just going to be top of an and, which is why I kept trying to write a middle bar through it. Yep. Then, this is our AND, so P and Q. P and Q is true when P and Q are both 1, otherwise it's going to be 0. So the way we can represent this is with a truth table, which has P, Q, P, and Q. And you can say 0, 0 is going to evaluate 2 for P and Q. 0. Feel free to join in, by the way, Nandini, because I know you like to join in, and there's not many people here, so you may as well. 0, 1. Nandini.
I think I'm more competitive than Joe this time.
Yep, 0.
More confident, what are you saying?
1, 0. Alex.
Not making a difference.
1 or 0.
1 or 0.
Yep.
And
Oh, and. Oops. 1 and 0.
Hang on, P and Q.
Yep.
Sorry, I'm out of it.
That's all good. 1 and 0.
2. And, as you know,
Sorry, rest in peace, headphone users. It's going to be 0 because we're looking at this this weird thing over here where it's like it's a pump that requires, or like a series of tubes that require both of these to be true in order for this to be true. Otherwise, it's going to be 0. Imagine it's like some kind of circle or some kind of water pipes.
So do they both have to be the same, or is it just both?
Yeah.
I know.
So there is no, it's not a sameness thing. It is either 1 or 0. So they both have to be true. You have to have 2 trues. So, and this can be seen with when you do logic and short circuit logic in JavaScript, and also I think you can do short circuit logic in Ruby as well. Yeah. So that's if you do the like 1 and 1, or like condition and condition. It's only when they both evaluate to true that full statement evaluates to true. And whichever one it reaches that's false first, it will just stop at that point. Cool. So that's our 1 and 0. And how about our favorite, the 1 and 1? 1. So this is the magical thing for ands. Ands 1 and 1 is the only time where it is true. Let's extend our truth table a little bit. Let's add another one over here, which is like makes it a little bit weirder. What do you think we'd be getting if we said not P and Q?
The opposites of every single
1, 1, 1, 0. Yeah? Cool. Not just flips the bit.
what's the not symbol on the outside?
So not is denoted as,
7, so
okay, it's probably, if I had to write it as neat as possible, it would be like that, right?
is that supposed to be
That
a
is,
total right angle or just a sideways
It-
split 7?
it is a total right angle. It is like, if you want the symbol, I'll go to the textbook. It looks like this. Whoa! Or it's gonna, yeah, there we go.
Okay.
Can you see that one?
Yep, I saw it.
Yeah.
Before it went away.
That's your not.
I would just use the exclamation point.
Whoa! Okay, cool, we're back here. That I'm gonna set or define as not. Not, how about not P and Q? Is that the same as what I wrote before? No, it's not, because I'm saying not P and Q. It's order of operations. It's like, if I threw brackets around it, then it would be saying not P and Q, but instead it's saying not P and Q. So what do we think it might be here? So, okay, this is doing a lot all at once. We can actually break up truth tables, and I encourage you to do this if you're ever working one of these problems out. You can break up truth tables into more parts if you need to. Whoa. For example, not P. We'll do that one now. So we've found our answer for this, so we're all happy with this now. We don't need to worry about that. Not P, and now let's think about not P and Q. So first we'll solve not P. So not P will be 1, 1, 0, 0. You can see because we're flipping the bits from over here, and then we can say not P and Q. So 0 and 1. If we look at 0 and 1 is going to be 0, 1 and 1, 0 and 0, 1 and 0. So 0, 1, 0, 0 is our not P and Q. Yep, capiche? Sweet. That's our and this is a truth table. Now, when we get to like, I guess, more extended statements about logic, I really recommend finding little chunks that you can break up and then trying to solve them with truth tables and then working it into an overall larger formula, because you can treat each part of the formula breakup as just some kind of abstraction. For example, the not P here, we can just say like R is not P, and then we just have to, and then all we have to do is just like imagine that this is just R and Q now. And that can be entire, like, large sections of a formula. You can just totally make the whole thing disappear and condense it into a single little thing that you have to keep track of again. But let's move on to OR. OR is sort of it can be A or B, nope, P or Q. As long as one of them is true, then they're both true, or like the output is true. So how would we show this? Let's just jump straight to the truth table this time. So we've got our P, we've got our Q, 0, 0, 0, 1, 1, 0, 1, 1. Okay, so which of these is going to be false?
0, 0.
Just 0, 0. Because if it's 0, 1, then it's 0 or 1 is true, which is true. 1 or 0 is true. And 1 or 1 is true as well. And that's like B, let's say, like saying something like, I want a Tim Tam or a cookie. It's like, you know, you can have both. That's fine. We're all happy with that. I may have been picking out on Tim Tams at the end of my lunch break, so they're still on my mind. There's another type of OR though, and that is called exclusive OR. So let's have a look at exclusive OR. Exclusive OR, for those who want to go a little bit nerdy out on it, exclusive OR, which we denote with an O plus, is the same as saying, so P XOR Q is the same as saying P or Q and not P and Q. So that looks like a lot going on there, but all you're saying is that it's only true when one of them is true, but it's not true when they're both true.
You have to choose a Tim Tam or a cookie.
You have to choose a Tim Tam or a cookie. So if we were to look at this one here, and we were to say, let's change this to a P XOR Q, which one of these lines is wrong? Yeah, exactly. Hold on, Joe. It's the bottom one. It's this one. This should be a 0 now, because it is 1 XOR 1, like true XOR true. We can also write these as all trues and falses. Yep, so true XOR true is false. Also, I don't mind whether you write ones or zeros or trues and false or T and F, as long as you have the same style across the whole thing. So as long as you settle on writing T's and F's, trues or falses, and ones and zeros, and have a mix of both, then it's fine. But a worded example of an XOR, written like XOR as well, that's what this is. A worded example would be something like, oh, actually, I've got it in the textbook, but one of my favorite ones of this is when my nan asks my pa if he wants tea or coffee, and he's a little bit deaf, so he just says yes. So tea or coffee, that's like saying tea XOR coffee. Just mixed together. The wild concoction, as they call it. There's a cool little diagram here. It's very messy and you can't actually see what it has any of these, but you can see that it's sort of like XOR and OR gates all the way down. And this is what's called a Leyden-Fisher adder. So the weird thing about what's going on here is that each of these, wait, can I do writing all over this stuff? Can I scribble? Does it let me scribble? I think it might. I don't want to draw a straight line, I want to scribble. Nope.
What about that circle at the bottom?
Circle at the bottom, I think that's drawing a circle around stuff. Ah, yeah, that is drawing a circle. If I get a highlighter, that's highlighting text. No, I think I can only draw a straight line.
The green thing looks like squiggly.
I can do this, but I don't really want to. Oh well, I guess that's that then.
What's the green thing? Green pen.
Green pen, that's... Oh, freehand line! That's the thing! Okay, cool. I was going to say, so if you have a number in binary, if you have a number in binary, say 0.
Wow.
Well, it's really metal. That's all we've learned about this. Super metal lines. If you have like 0, 1, 1, this is going to be too frustrating. If you have like a 0, 1, 1, 0, and you're adding it to a 1, 1, 0, 0, which is going to be what? So this one's 6. This one's, we've got a 8 plus a 4. Yep, so 12. Actually, this is going to be a fairly big number. So let's go 0, 0, 1, 1, and 1, 1, 0, 0. If you're adding those two numbers together, you actually are putting the bits of each one into each of these opening bits here, and then it's calculating your answer as a single value. So you start with two 8-bit numbers, and you put them together, and you get one 8-bit number as a result, and that is actually how you do a mathematical add on a CPU.
That's
Yeah.
half added and full added.
Yes, and there's a fun little tool online called the NAND game, and yeah, not this NAND. And you can actually build these yourself. You can build adders, and you build all the components that lead to the adders and everything, and build all the parts up. So that's a little fun thing. Side note, I can link people if they're interested in that. But yeah, that's kind of how CPUs do stuff. So the other day, remember when we looked at bases, we were thinking of memory as being a string of bits in different kind of boxes and stuff. Like when you have a number like a 7 or whatever, you have your 0, 1, 1, 1, and that's actually a thing there, and that's actually the number 7 stored in memory, and we're also looking at it as hexadecimal, which is how you represent it. So those numbers actually get just lifted and put into the CPU, and then just get dumped through these adders and stuff, and then whatever comes out the other end, they'll then put them in a different spot in the memory, and that's now we've got our storage and we've got our operation. So how crazy is that? Just through a little bit of discrete math, we've looked at a very major fundamental of computing, and now I've lost all my stuff. Oh, there we are. Back to the drawing board.
And just on a quick note,
Yep.
multiplication for us is also added for the CPU.
Yes. Yep.
There's nothing like multiplications on this added.
Yeah. There are some cool weird ways of doing large number multiplication, but you still use small multiplication, which is using these adders and stuff. So when you multiply really large numbers, you actually break them down into weird little hacks you can do with multiplying smaller numbers together and then assembling the whole thing. And UNSW and a Israeli university just published a slightly more efficient way of multiplying at the end of last year. So when we get into big O notation, I'll tell you how exciting it is that we moved from, I think, O something blah, blah, blah to O log n multiplication speed. But at the moment, it is just all gibberish, isn't it? Okay, let's look at the next one. So we've done ands, ors, and XORs. Is everyone here like clear and or happy with all the things here?
Sure.
Clear, oh, it's not a clear XOR, they're not mutually exclusive. You're confused, XOR, you understand it. All right, let's move on to bit strings then. So this bottom bit here, bit strings. When I was just talking about adding things together, when I was talking about treating it as bits, how about we do that ourselves? How about we do logical operations on bunches of bits? So I'm going to get you guys to do a couple of these things. First of all, actually, yeah, no, let's just go straight to it. Imagine that when I write 1, 0, 0, 1 and 1, 1, 0, 0, I'm asking you to do an AND operation between each of these, then between each of these, then between each of these, and between each of these, and write the output. Okay? You probably did it while I was writing the question, didn't you? Gosh darn. And who on earth is buzzing me? Everyone's still good, it's getting my audio. Anyone need another moment?
You're too quiet today, Philip.
The lack of sleep finally didn't
Are you going to say something?
He's trying to work this out, I think. Who needs another minute? Another couple seconds? Alright, let's go through it then. Do you want to pitch your answer? Yes. Cool.
So this is P and Q, yeah?
Yep.
So 1 is 1. Oi. So difficult.
You can see the little
Ah.
cursor. Yep, nice.
And P0 Q1 is 0.
Yep.
0 equal 0. 0 plus 0 equals 0.
Yep.
And this is 0.
Nice. Yeah, cool. Good work. Now, good stuff. That's our and. Let's take it one step further. I mean, I can't write out this whole weird wacky thing when I'm typing it, especially. It's just going to make it frustrating. So I'm going to make this a little bit. I'm going to write this slightly differently. We're going to look at 1, 1, 0, 0, and we're going to look at or 1, 0, 1, 0 equals blah.
Previously, what we did was conversion from one format to
Hey,
another.
bless everyone.
This is
I'm born on the 12th of December. I am Jesus.
Alright, so everyone's done?
How are they connected to?
Yes.
So, Jenny,
Hmm?
one question here is, last week we did basis,
Mhm.
this week we're doing logics. How are they connected to each other, or they're...
Next question, you will see. Yeah.
Okay. So, or,
Do you want to write it?
no.
Wow.
What an asshole.
Yeah.
One,
So the question in the class is never do you want to write it, you have to write it.
Go up there.
I want to use the thing. This can't go well. So, if I'm correct, then anything with at least one would be true. This has to be one or the other one is true. So,
Can you see the little cursor flying around?
yes,
Yeah,
I do.
sweet. It's a
So,
little bit easier off the screen, so the monitor's a bit delayed. Yeah, nice. Yeah, sweet. Well done. So, yeah. See, that wasn't. It's not as weird and finicky as it could be.
yeah.
So we're happy with that. Is anyone a bit unsure about that one? I guess it's not enough of us to really be unsure about any of this. So let's look at one more. And this is where we will bring back our old friend bases. Let's try something like 13 XOR, let's say 7. Now, before I get you to start working through this, is the answer going to be odd or even? Yeah, it is going to be even. Because we know the last bit is going to be 1 in both of them, and 1 XOR 1 will cancel out and make 0, so it has to be even.
Are we changing this to binary first?
Yes, so the way to solve a question like this is, and this is how it's done as well, if you XOR between two numbers in like Python or Ruby or whatever, you must first turn it into binary, then you must XOR it. What should the result be in?
Well, if you're asking us in decimal, then it should be in decimal.
Correct. So this is sort of like a general sort of computing thing. If you perform an operation on a type, then it should generally return the same type unless that operation is explicitly converting it. So decimal XOR decimal should be a decimal, unless you're doing decimal to binary as the operation. I've had a lot of fun over the last few days introducing types in Python. There's actually inbuilt types.
Wow.
Yeah, but you have to use a custom Python compiler to actually do static type testing. But it was really filthy the first time we tried it because we couldn't figure out how to get the function type in there. So we ended up having to pull, create a function, save its type into a variable, so we could use that as our type.
Oh man.
Yeah, it's gross.
We need to bring in more TypeScript and C#. Make things good.
Yeah, absolutely. Well, I was thinking we do need to have do some type comparison types as well, so that people don't find it hard to move across. Back when the discussion of what the other language would be, but oh well. Does anyone want to have a crack at writing this up? You're having a quiet day today. Okay. Vow of silence or something. Cool thing.
I haven't done it.
Sorry.
I haven't done it.
No, that's
You-
not wrong.
Do the working. Do the working in front of us.
I don't know how to do the working.
First, you convert to binary, which you should be able to do. Can you do that? Are you fine with that?
Sort of.
Sort of. Okay. Okay. Well, how about you do the next one then? I'm guessing Joe, you want to correct this? Cool. So we'll do another XOR one a little bit. You're working. You have some time to work it out as well.
Where am I? There I am. Okay, so 13 in binary, 8, 9, 10, 11, 12, 13.
Mm-hmm.
X or
Hit me after this, Derek, that I'm putting you on the spot.
7. Boom, boom, boom. So X or it has to be 1 or the other, not both. So that's 1, 0, 1, 0, and that's 8 and 2 equals 10.
Woo! Sweet. Well done. Well done, Joe. So, yeah, that's exactly what we're doing here. Nothing more, nothing less. We're going to look at one more different sort of logic thing, and then we might just have a couple of these to work through, just to make sure we're all on the same page. Make sure everyone's up to snuff. And a lot of the challenges as well are just going to be the ones out of the challenges in the textbook. But the last one we kind of need is implies. Where are the challenges? There we go. So implies is another one, which is saying, let's say you have smoke and fire. I'm going to write smoke. So S denotes smoke, or we've seen smoke. I've written smokes, I mean smoke. F, we set that to fire. Oh, also, if you're curious about what this notation means, like the colon equals, it's the same as kind of assigning a variable. Like you're just saying, I'm setting this to that. You guys can write equals if you want. You can write a colon if you want. I don't really care. Or you can write S is smoke. I don't mind. This is just the way I like to write it. As long as before you do logic notation, you indicate what symbol represents what meaning, then you're fine. So we want to make the statement that smoke, when there is smoke, there is fire, but that doesn't necessarily mean that if there's no smoke, there's no fire. because you can have like, you can have like a blue flame, like a kettle or something, not kettle, a stovetop. But we want to say that if there's smoke, then there's fire. And then we'd write that as smoke implies fire. And the reason that there's an arrow here is because smoke is implying fire. When there's smoke, there is fire. When there's not smoke, we don't know whether there's fire or not. It's kind of this one-way thing. If fire also implied smoke, this would have a double-sided arrow, and that would be saying that when there's smoke, there's fire. When there's fire, there's smoke. It's kind of like joint. And that's saying that it means the same thing. It's saying they're logically equivalent. They'd be describing the same situation. But we're not doing that. We're doing smoke implies fire. Given this knowledge, let's write out a truth table. Now, this is a little bit different from the other truth tables. The reason being that when we've looked at things like 0 or 0 and 0 and 0, those have generally output as 0, and the reason being that you have two non-inputs and you get a non-output. Like there are two falses, you get a false. In this case, it's a little bit different, because what we're looking for is a time where the P and the Q, whatever the P and Q are set to, or S and F in this case, whatever they're set to, doesn't actually work with the description, the logical description we've made. So we've got S and F. We'll say S, we'll say F, 0, 0, 0, 1, 1, 0. Let's make that very clear. So 0, 1, 1. Yep. And now we've got our statement S implies F. Now I'm going to go right out and say that this is true. The reason being that you can say there's no smoke and there's no fire. So this is fine by the implies logic. So this is the one thing where you can have 0 and 0 as the two inputs, and it can be true, is implies. I mean, if you have some knots thrown in there and stuff, you could flip an output so that it was true. But generally, like ands and ors and XORs, 0, 0 will always be false for those ones. But we've got our 0, 0 as true. Okay, how about...
What exactly does that mean in our analogy of smoke and fire?
That's saying there's no smoke, there's no fire. 0, 0. So why is it 1?
1, yeah.
Because you're saying that statement works. That statement's true. That statement's fine according to the these things both being false agrees with the statement we've made. It doesn't contradict our logic. That's why implies is a little bit different, right?
So as long as the evaluating expression returns to true, it'll be true?
As long as it makes sense.
Yeah,
As long as it makes sense. As long as it doesn't contradict the statement we've made. Cool. So how about there's no smoke and there is fire?
0.
That's fine. You said you can have fire without smoke, is there?
Okay. So who thinks that 0 implies 1 can be fine? Like as in S, as in this case here. So 0 implies 1. Who thinks it's fine? Who thinks that this is going to be false? Okay. So I'm going to put it into just words and see how it feels now. There is no smoke, but there is fire.
Yes.
So when I said smoke implies fire, there is no smoke, but there is fire. That's actually fine. We're happy with that, and that's the whole one unidirectional thing of it. So that's the whole. You can have fire without smoke, but you can't have smoke without fire because smoke implies fire. Yeah, that's why there's one direction there. And this actually is a really interesting thing in logic, because when you hear someone make a statement like smoke implies fire, your brain will say, okay, then fire implies smoke. Your brain will tell you that it should be universal, and a lot of people use this to sort of like pass off logical fallacies where they'll try and lead you being like, well, every time it rains, the trains get busier, so next time it gets really busy at a train station, better bring an umbrella. Like, that kind of statement. It's not true. It doesn't, you can't flip the direction of the logic. Yeah? Does that make sense?
Indeed.
But there might be something like people carrying umbrellas. That's not an implies, because if people carry umbrellas, that implies it's raining. But if it's raining, that implies people are going to be carrying umbrellas. So that's actually both directions. So rather than being implies, in that case, that would be raining umbrellas would be this sort of stuff. And I regret giving you that example, because I think there's a question here that directly makes that confusing, but we'll get to that. We'll get to that when we get to that. There's a little bit of a gotcha there. So we've got our implies. There's one more way of representing implies for people that didn't click with on the first run, and anyone who might be, well, there's any viewers listening at home, and that is that if we represent it like P implies Q, I like to think of it as a big old circle. And inside that circle is a littler circle. This little circle is called P. This big circle is called Q. And if there is an X inside of P, then it's going to be inside of Q. That is implies. So can I draw a dot? Let's get our little table up. P implies Q, P, Q, P implies Q. Can I draw an X that is in neither of these two circles on this page? Yeah. Can I draw a circle which is inside of, let's say, inside of Q but not inside of P?
Yes.
Yeah. Can I draw a X that is inside of P but not inside of Q? Ah, shit. That's the one that we'd say is false, or 0 in this case, because we're writing ones and zeros. And can I draw an X that's in both of them? Yeah, because if it's in P, then it's in Q. So that's our 1, 1, 1. Yeah. That is another way of representing it.
Hang on, according to that, we just said if you drew it inside P, that it's also inside Q, but then the one before, oh no, that's, no, go on.
Yep. This is all fine?
Yeah, I like how this is done.
Sorry?
It's easy to remember this one.
Yeah. For people who are a bit more visual like myself, this can make it a little bit easier.
Yeah.
Yeah. Cool. Let's say we're happy with that for now. We've looked at implies. We looked at implies and we looked at all these other logic statements. I might get y'all to have a crack at some of these challenges. Yeah? Cool. Groovy. We'll take so what time do you want me to go till today, by the way? As in, like, I can fit sets into this session as well, because these are both very short sessions, so I can...
How long did it take?
Same amount of time as this. So this took about 40 minutes or so. So sets we would go until about 3:30, maybe 3:50. So I don't know. I'm gonna pause the recording for this admin discussion. You guys start on your challenges, and I'll just